using this little handy dandy mic over here. We're going to see how it goes. Could go well, could go bad. We will find out. All right. So lesson 1, fundamental counting principles. So the curriculum outcome we're covering is solving problems involving the fundamental counting principle. And, oh, I didn't tell you this. I'll leave it on the thing anyways. I have 2 daughters. They're in grade 1 and 4, and it's their first day today. And one of them is London. That's why I thought of it. I put their names in here. The other one's Isla. And so London is 6, and she is shopping for a sports utility vehicle. Because why not, right? The dealer says that she, most of the time when they see her name, they ask how he's doing anyway, so we're good. But she has 3 different models, Bronco, Explorer, and Expedition, and that each model is available in 5 different colors, gray, brown, white, black, and blue. So we're going to do a tree diagram to show all the different outcomes that we could come up with, all the different types of cars that Lennon could buy. So when you go to put the model down, please leave spaces between the words. If you don't, you're going to be erasing and redoing because you're going to need spaces to make branches off of it. Okay? So we have Bronco, Explorer, and Expedition. So if that was the only options I had, yeah. Make your hand then. Yeah, I can. You go. This is only when it's weird. Then I have to do this, then I have to sanitize, then I have to do your sheet. Yeah, this is when it's being super weird. It's just for you. And this takes like 700 years. Oh, it's been recording this whole time. That's awesome. Whoever misses out gets to really listen to great things. All right. So we have a Bronco, Explorer, and an Expedition, so that would be 3 different kinds, right? Okay. But it's not just that. Each vehicle then gets to be chosen in 5 different colors. So off of each of these, so we have the model at the top, we're going to have a color. Off of each of these, we're going to have 5 little lines, right? So we're going to have 5. This we're going to have 5. So we're going to have gray, brown, white, black, blue. So now instead of having 3 outcomes, which would be the Bronco, Explorer, Expedition that London can choose, she now has how many she can choose? 15. She's lucky. You don't even need a mask because you have no one near you. And you're properly distanced from her. Just today, though. Tomorrow, you're back to masking. Yes. So you would have 5, 10, 15. We'd have a Bronco in gray, a Bronco in brown, a Bronco in white, a Bronco in black, a Bronco in blue. Explorer in gray, Explorer in brown, Explorer in white, black, blue. Expedition in gray, brown, white, black, blue. So we would have 15 different SUV choices. Which is time consuming but not awful. right? You could still show this. The reason why we show the tree diagram is for probability unit, so that we can see all the different outcomes, but also the reason why is so that when I show you the fundamental counting principle, you believe me that we do get 15. Okay, because here we saw we got 15. Now, how mathematically could we get 15? What math could we do to get this? Yeah.
Times the 5 multiplied by 3.
Yeah, exactly. So here we have the model, and there are 3 of them. And we can times it by the colors, because we're taking each of them and physically multiplying them by 5 colors, right? So 3 times 5 is 15. So that's on this one down here. London has 15 choices. It should be London has. And then this would be your answer here. How do you use these numbers to arrive at that answer? The number of choices there are for the model and the number of choices there are for the color. Now for C, it says that the dealer tells London that each of the SUVs comes in 2 editions, SE and LE. So now how many choices would it be? 30. Yeah. Because you would have your model, which there were 3, times your color, which there was 5, times your addition. Because you get 2 more branches off of each of those answers, right? We had 15 answers before. I know each of those 15 answers would get 2 more branches. So we get 30. Make sense? So this is the fundamental counting principle. It's saying when you take one part of each, and you take the choices that each one has, you can multiply to get the answer. So for example, I'm taking one model, I have 3 choices. I'm picking one color, I have 5 choices, and I'm picking one addition, but I have 2 choices, right? Then you get the total. So that's where this comes from. The fundamental counting principle can be extended in more than 2 tasks. If one task can be performed in A way, and another task can be performed in B ways, and another task can be performed in C ways, and so on, then you can take the number of each task and multiply them and get the total. The fundamental counting principle applies when tasks are related with the word and. So whenever you see the word and, or you can say the word and, like I need to have a model and a color and an addition to get a whole car, right? So if we say and, we're going to know to multiply. So if we look at the your turn, I'm going to help you get it set up because some people will set it up wrong. If you have a toy manufacturer makes a robot in 3 parts. So we have part 1, where you have to pick one of them. The head can be red or blue. Part 2, you can pick 3 of them. The body may be orange, white, or black. Part 3, you can pick 2 of them, purple or pink. So we have to set it up more like, instead of a tree diagram, it's more like a shrub. We work out sideways instead of up and down. So we would have part 1 labeled, just like that other one we had model labeled, right? And then we're going to write the 2 part colors below. Red with space and black. Oh, blue. Right? And then what would we do next? Off of each of these, I have the option of a body, which is orange, white, or black. So I have 3 options. So I'm going to label this part 2. So you finish this. You're going to finish the tree diagram and do the fundamental counting principle, which is the blanks. So for part 2, we had orange, white, black. And at this point, if we stopped, if we didn't need the shoes, we would have 6 different toys we can make, right? But we do have shoes. So we have a part 3. And off of these, we each have purple and pink. So instead of 6, we actually have 12, right? So if we go to show the fundamental counting principle, we're going to do, we each have to choose 1 from part 1. We have to choose 1 from part 2. We have to choose 1 from part 3. If we had to choose more than 1 from each of those things, we couldn't use the fundamental counting principle. Okay? We have to use something else, which we'll learn later. So we have 2 options for part 1, 3 options for part 2, 2 options for part 3. And what you need to do, and what you'll find that you might stop doing, is putting the little dots. Because the little dots mean multiplication, right? So if they're asking you to algebraically show how you would get this, if you don't put the dots, you're not showing algebra. You're actually just showing the number 232, right? So we multiply, and we get 12 different colored robots. And we always write a statement, so we don't lose marks on the written response. Because what sometimes you'll find, and I'll find until I ask for sentences, people can get answers perfectly, they just actually have no idea what they found. So the sentence fact makes me understand if you actually know what you found or not. Okay, you're going to try this one on your own. I have to unfreeze it. Still fresh. Okay, so with the tree diagram, you would have went Jersey, and you would have went red, black. And then you'd go pants, white, red, black. White, red, black. And then you do socks. So how many different outfits? How many different weeks? 6. That's how you're angling yourself. 6. To the classroom of no one. Okay, so yes, you are right. So it'd be 6 weeks. And we can show it with fundamental counting principle by going, now this is, if you can keep this in mind, you'll get every single one of these right. I am choosing 1 jersey. Why is this thing rattling? 1 pants. 1 pair of socks. And I have 2 options, and I need pants, so I have 3 options, and I need a pair of socks, so I have 1 option. So I have 6 weeks that they can play, right? So they get a matching outfit. So if we flip to the next one, it said here, what is the probability of wearing a color rush outfit? A color rush outfit in the NFL, if you don't know, is one where all the colors are the same. So it's when you look at the NFL and you're watching them and you're like, why are they all freakishly in blue? Or like, why are they all in orange? Bright orange. It's a color rush color. And some of them I think are really cool, and I think some of them are really ugly. But, you know, the baby blue ones are really cool. So what is the probability of a color rush outfit? And probability is in 2 more units, but I want to show you how they will use the units together. So they're going to use this information we know, so we need to know this really well in the probability unit. So how many of these, when we go back to that tree diagram, how many of these are an outfit with all the same color? Cody? 1. And how many out of total? 6. So we have a probability 1/6 of fitting a color rush outfit, right? Not a hard question. But you need to know the first part, information from this unit, to be able to answer it, right? Okay. Jeremy wanted to go shopping for pants to make sure he had enough different outfits. An outfit must have a shirt, a pair of pants, and a pair of socks. Just one of each. To not repeat the same outfit for 48 days. So he's going to be washing his clothes a lot, don't get me wrong, but not having the same outfit. So same pair of socks, the same pair of pants, same pair of shirt. Same pair of shirt. Yeah, same shirt. So in his closet, he has 8 different shirts, 2 different pairs of socks. How much pants must he buy? I'm going to let you guys see this question. You have not seen a question like this because I've never given you one where I gave you the total, which is 48. But you have the information to easily be able to solve this, right? So we want to be able to see a diploma question and not freak out, or see a unit test question and not freak out, knowing I know the information behind this. You just have to think a little bit. Okay, so you're going to try this question. Record. Jeremy, so how do we do this? So we want to set it up. You guys are really into this. I like this. This is good. Okay. Who wins? I don't even know. One of you was faster than the other. Oh, he said you were up. You're faster. Yeah. What would we do? Help me set this up. Oh, that's not going to help me. Okay, Cody, did you do the same thing? Okay, how would you set this up? You know how to write it. Put your mask on and then you can answer. Please. You have so much information to tell me. I really want to hear it.
I did 8 times A times 2 equals 48. And I just moved everything to one side.
So you went 8 for the shirts.
Yeah.
And then you went
A for pants.
A for pants.
Yeah.
And then you went
2.
You used a variable?
You're not supposed to?
No, that's amazing. I'm like, no, I'm proud. Like that, no, just, you won. You're winning right now. Yeah. And 2. Like, I would have taken just a blank that was empty, but a variable, like, and then you solved. My day can't get better. It's pretty much, you moved the stuff over and solved. Yeah, I'm going to do that. So then he said he got 16A, or he did something else, whatever. And then he even moved it over.
Yeah, I moved it over.
By dividing, and got a 3. Now this is like the perfection of perfections of how to solve this. But if you just went 8 times 2 is 16 times what is 48 is 3, that would work. Or if you did it in your calculator. Because it's a numeric response, no work needs to be shown, right? But I wanted to go through how we do it. Yeah.
Is it a problematic thing if you go like kind of the opposite of how you did it, just like 48 divided by 8?
Nope, because you're doing the same thing. Yep. So we put a 3. And we fill in left to right, correct? Not right to left. You fill in the way you read. And you don't need to fill in all the boxes. So I get some people going 3.00. The boxes do not need to all be filled in. It's actually wrong if you do fill them all in this case. Okay, we're going to look at example 2. So we have a math quiz of 6 multiple choice questions. So how many parts are to this math test? 6. So we're going to write ourselves 6 lines because there's 6 parts. 1, number 1. 2, number 2. Number 3. Number 4. Number 5. Number 6. Okay? We have 6 parts to this. So we're number 1, 2, 3, 4, 5, 6. Correct? Now we need to do number 1 and number 2, and we have to do multiple choice 3, and we have to do 4, and we have to do 5, and we have to do 6 to do this test. So because they're ands, we multiply, right? Now we're only going to have 1 correct answer for number 1, 1 correct answer for number 2, so that's why we can do the lines, right? Because it's 1 correct answer, 1 correct answer, 1 correct answer. Above the lines, we list how many options we have. So here it says each question has 4 choices, A, B, C, or D. So number 1 would have 4 options. Does that mean I'm choosing all 4? No. The blank shows I'm choosing 1 of 4, right? Number 2 would be 4. Number 3, I'd have 4. Number 4, I'd have 4. Number 5, I'd have 4. Number 6, I'd have 4. And so people tell me that's 4 times 6, which it's not. It's 4 to the exponent 6, right? Or 4 times 4 times 4 times, like you typed it in that way. So if we type it in, we're going to go 4 to the exponent 6, or 4 6 times. So it's 4,096. Yes. So the people who believe that they're going to guess without studying, again, get 100% on a 6-question multiple choice test, you have a 1 in 4,096 chance. And then people are like, there's no way there's that many answer keys. There actually is, because I could go all A's, and then I could go all A with a B, I could go all A's with a C, all A's with a D, right? Then I could do all A's to here, A, and then B, A, you know, you can swap them around. So there's lots and lots and lots of solutions. So how could I write this as a diploma style question? Well, I could change it up. I could say that Mrs. Lepp went to go mark a 6-question multiple choice quiz. Okay, she went to go mark it. She had her answer key sitting in front of her on her desk. All of a sudden, she accidentally knocked over her coffee, and her coffee spilled, and it washed out numbers 3 to 6. So the answers to number 3 to 6 are all washed out. 1 and 2 are still there, right? You try it. What would it be? Try it. 1, 2, 3, 4, 5, 6. I gave you 6. You have 6 blanks. Numbers 3 to 6 got washed away, but answers 1 and 2 are still there. Try it out. Do fill in the blanks. See if you do. So you're gonna have 6 blanks. Which do we know the answers to? 1 and 2, correct? So for number 1, some people are like, well, I don't know what it is. It could be A, B, C, or D. It doesn't matter. It could, yeah, you're right. It could be A or B, C, or D on that sheet. But it is one of them, is it not? So how many options do I have for this blank? 1. It's 1. Because if you look at the answer sheet looks like this. I have answers here, right? They could be D, they could be B, it could be A and A, it could be whatever. But we know what they are. And then these ones are washed away. So these ones could be A to D. These ones have to be A, B, C, or D, right? So they're going to be one of them. We can see what it is. So I have one option for this one. It's either D or it's C, or I can literally see what it is, right? It didn't wash away. For number 2, I also still only have one option because it didn't wash away. Then for 3 to 6, I have 4. So that's 4 to the 4. I don't remember what that is. Donk. So much less chances of getting different answer keys, right? Because I knocked out 2 of them. I told you what they were. So because I knew what these 2 were, they're restricted to being 2 specific answers. I have to deal with those first, and then I can deal with the rest of the question after, which didn't have restrictions. So we're going to look here. How many odd 4-digit numbers are there? How many odd 4-digit numbers are there? So we need to go through what the heck the definition is. So I'm going to get you to raise your hand if the number I say is odd, and I'm going to get you to not raise your hand if the number I say is even. Ready? So raise your hand, odd, don't even. 29. 28. 27. 26. 25. 24. 23. 21. 759,357,493,271. The only thing you listen to is the last number, right? The last digit. So in order to know if something is odd, the last digit has to be odd. That's it. Did it matter what I said before that in that big long spiel? No, it didn't matter. So if it says odd, that indirectly tells you that the last digit must be odd. So when it says odd, I know the last digit in that 4-digit number has to be odd. Okay? Now 4-digit numbers. You can put down your pencil for a second. I'm going to open up a new page. Okay, so I'm going to pay you in 4-digit number. I'm that nice. Okay, I'm just going to pay you for being here. not. Let's pretend that. Okay, so here, I'm paying you in this 4-digit number. Wait, I'm going to pay you in this 4-digit number. Wait, I'm going to pay you in this 4-digit number. This one's better. What did your elementary teachers teach you about zeros in front of numbers? There's nothing there. They don't need them. They're not a placeholder, right? If I went 70, I need that 0, correct? Because that place holds the 1, the ones place, right? But if I have 070, that just looks silly unless it's a code. So you can just erase it, correct? So this number is actually a 1-digit number, isn't it? With a whole bunch of zeros in front of it. This one is a 2-digit number. This one's a 3. Could I do this? Would that be a 4-digit number? Yes. So what was the problem with all of mine? They started with the number 0. So if they start with a 0, they're just a hidden digit number with zeros in front, right? So this back here, I'm on it, I forgot. If it says 4-digit number, that's another thing that's saying cannot or can't begin with a 0. And it must be a 4-digit number. If it's a 4-digit code, can it start with a 0? Yeah, a code could be all zeros, right? Because a code doesn't matter. A 4-digit code is a placeholder for the code. So if you see 4-digit code, some people will fall for this and say, oh, it can't start with a 0. That's not true. A code could be all zeros. A 4-digit number cannot start with a 0. Okay, so it's a 4-digit number, which means it's going to have 4 parts to make this number, right? 4 single digits to make a 4-digit number, correct? So we're going to go 1, 2, 3, 4. Now we must deal with the restrictions first. So the things that are being restricted have to be dealt with first. So I know that the front number can't be a 0. I know the back number needs to be odd. The middle 2 digits, there's no restrictions on them, right? They can be whatever. So I have to start with the back or the front, but I can't start with the 2 middles. I have to start with the restrictions first. So I'm going to start with the back. It can be the digits 1, 3, 5, 7, or 9. It can't be 11 because 11 is actually a 1 and a 1. It's not, right? The only thing I can put in these blanks are single digit numbers. So I list my options below, and the number of options goes above, right? That's what we've done the whole time. The number of pants went above. The number of socks went above. The number of robot heads went above, right? So how many options do I have here? 5. So I'm going to put a 5 above. Does that mean that this number actually ends in the number 5? No, that represents nothing about what the number ends in. It represents how many options I have, right? This number could end in 1, 3, 5, 7, or 9, actually. I don't know which one, but I have 5 to choose from. Now I go to my front blank. My front blank, I told you, it cannot start with a 0, so it has the options 1 to 9. Do you know what's the saddest thing? People not using their fingers and giving me that wrong amount of numbers, that is. So count it out in your hand. I'm totally fine with that. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 of them. Okay? 1 to 9 is obviously easier, but you might end with 2 to 7 or 3 to 6 at some point. So count them out. There's nothing worse than getting it wrong just because you didn't use your fingers. I would rather you use your fingers. Okay? So we have 9 here. Now there's no restrictions on the middle, so they could be 0 to 9. Correct? And 0 to 9 is actually 10 options. Now, does this mean that the number is 9, 10, 10, 5? No, it absolutely doesn't mean that at all. It means I have 9 options for this first blank to make this 4-digit number. I have 10 options for the second blank to make this 4-digit number, 10 options for the third, and 5 for the fourth. And I have to remember to put my multiplication dots. And so I'm going to get 4,500. So there are 4,500 odd 4-digit numbers. Now B is basically the same question, but with no repetition. So, how many odd 4-digit numbers are there with no repetition? Now, when you see no repetition, what you're going to do is box and hold. So you're going to still do the question the exact same, but you're going to box and hold the number there so that when you go to do the next blank, you've pretended you've used that number up already, so you can't repeat it in the next one. So for example, we're not going to be able to have the number 1011, right? Not going to be able to have the number 4066. All those are going to be kicked out. Well, 4066 is evens. Kicked out way before it even started. I don't know, I get like 4055 would have been a better option. Okay, so we're going to go with 4 blanks. Okay? We still can only end in a 1357, 9. That didn't change. 13579. But when it says no repetition, I always do this one extra step, which is box and hold it. Okay? So I'm going to either box the 1, 3, the 5, the 7, or the 9. I'm going to pretend to hold it. I either always box the 1 or the 9 because I'm lazy. And in the next one here, I want to go 1 to 8. If I pick like the 3, I have to go like 1, 2, 4, 5, 6, 7, 8. I'm lazy. I just want to write it short form easier. So I'm going to box and hold the 9. But could I have done any of the other 4? Sure. Does that mean I'm guaranteeing the 9 is staying there? No, I'm just using it so that when I go to list my options below the other ones, I don't forget to put it. Okay? So, or I don't forget to not put it. So I'm going to put 5 options here. Then for the first one, it can't be a 0. It can't be a 9. Technically, right? So I have 1 to 8, which is 8 options. And then I have to box and hold again. So I'm going to pretend to hold the 8. Now this is where the error is going to go. You're going to say 1 to 7, and that's 7 options. 1 to 7 is 7 options. That is true. But there's a catch. So in the back, and this only works with odds, okay? The back 5 digits didn't use the number 0, did they? They couldn't. The front blank didn't use the number 0, did it? Because it couldn't. But can the second blank have a 0? Yes. You have to remember to bring this 0 back and say there's actually 8 options. If you're someone who wouldn't have done that, make sure you circle this and off to the side write a little note for yourself that says, don't forget to bring the 0 back when it's not repeating. When it's an odd non-repeating. I would go over here and I would go like this because these are my notes for me to study from. Don't forget to bring the 0 back. When odd and not repeating. Because the key part here is that it's not repeating, right? Because we still brought the 0 back on this one, it was 0 to 9. Now I'm going to pretend to hold the 0, and then it's 1 to 7. I need 8 times 8 times 7 times 5. 2,240. Does that seem realistic? Our answer before was 4,500 for all odd numbers. Now I'm taking out all the repeating, and it's a little bit, it's below half. Yeah? If you took out all those repeating, it takes out a lot. Okay, I'm going to give you one to try. How many odd 6-digit numbers are there? Did I say no repetition at all? No. So if I don't say no repetition, you assume you can repeat. They aren't going to say we can repeat. Okay? So how many odd 6-digit numbers are there? And then your second one is how many odd 6-digit numbers are there without repetition? Try those two. So 1, 2, 3, 4, 5, 6. This one doesn't say not repeating. So our back numbers can be 1, 3, 5, 7, 9. We have to deal with restrictions first, so we deal with that blank. This one can be 1 to 9. It can't be 0. So that's 9 options. And the middle has no restrictions, right? So we could have 0 to 9. So 450,000. So a few more odd digits when you hit 6. Now, how many are there without repetition? 1, 2, 3, 4, 5, 6. We're going to have 1, 3, 5, 7, 9. Then we do the box and hold. So I'm going to hold the 9. Still have 5 options. Then here I'm going to have no 0, no 9, 1 to 8. So I'm going to have 8 options. Then I'm going to hold the 8. And then I'm going to have 1 to 7. But I have to remember to and bring back the box outs in basketball. 0. And you're going to get a 8. And then 7, 6 again. If you want to show your work so that you can get marks, if say you screwed up and it was a written response, I would show them. Also, the people making mistakes are much more minimal when they actually do this part. Yeah.
For questions like this, every time it's repetition, would those first two numbers always be the same, then it just goes down by 1 until you get to the end?
Yeah, if it was this particularly exact same question, yeah. So, we have 8 times 8 times 7 times 6 times 5 times 5. 67,200. So it dropped substantially this time than last time, right? But it's more numbers that you could have repetitions with. That is it.